Hello students, welcome to the class for fluid mechanics, BMM2533. So for today's class, we are going to start our new chapter for week 5, which is fluids in motion, or which is related to fluid dynamics and fluid kinematics. So starting with the slides, perhaps, these are this chapter or fluids in motion is basically chapter number 4 and chapter number 5 for your book, and your book is Senjal Simbala. So you may refer to chapter number 4 and chapter number 5 for your chapter. So what are you going to learn in this chapter, fluids in motion? So in fluids in motion, first of all, you're going to look around what are the descriptions about fluid motions, what are the different types of fluid motions available. Then you will learn about what is laminar and turbulent flow, what is control volume, what is a system. That you're going to understand about continuity equation. This is all what we are going to cover in the first week. In the second week, we are going to go through the energy equations which are related to Bernoulli equation. And in the seventh week, we will be covering the momentum equation. So before we start, we need to understand what is fluid kinematics all about. So fluid kinematics is basically concerned with the study of motion, and fluid kinematics is basically study of how fluid moves around, how they behave when they are under motion. So there are basically various ways by which we can define fluids, and there are basically many approaches. So that is also something that we are going to learn. So for the first topic, which is description of fluids in motion and control volume, we are going to cover this topic in today's class. So let's move forward. So in this today's class, you will be learning about different types of fluids in motion. Fluids such as internal flow, external flow, steady and unsteady flow, uniform and non-uniform flow, laminar, transitional and turbulent flow, and then the approach is Lagrangian approach and Euleran approach, as well as what are path line, streamline, etc. So these are something that you will be learning. So before we move on, let me give you a brief introductory video. So please go ahead and watch this video.
Types of flows are steady and unsteady flow, uniform and non-uniform flow, laminar and turbulent flow, compressible and incompressible flow, rotational and irrotational flow, 1, 2 and 3-dimensional flow. Let us discuss these types one by one. The flow in which fluid characteristics like velocity, pressure, density etc. at a point does not changes with time is called steady flow. For example, flow of water with constant discharge through a pipeline is as steady flow. The flow in which fluid characteristics like velocity, pressure, density etc. at a point changes with time is called unsteady flow. For example, flow of water with varying discharge through a pipeline is unsteady flow. The flow in which velocity at a given time does not change with respect to space, that is length of direction of flow, is called as uniform flow. For example, flow through a long straight pipe of uniform diameter is considered as uniform flow. The flow in which velocity at a given time changes with respect to space, that is length of direction of flow, is called as non-uniform flow. For example, flow through a long pipe with varying cross-section, is considered as non-uniform flow. The flow in which the adjacent layers do not cross to each other, and move along the well-defined path is called as laminar flow. For example, flow of blood in small veins, flow of oil in bearings, flow of highly viscous fluids etc. The flow in which the adjacent layers cross each other, and do not move along the well-defined path, is called as turbulent flow. For example, flow through a river or canal, smoke from chimney etc. The flow in which the density does not remain constant, for the fluid flow is called as compressible flow. For example, supersonic flow, flow of air in turbo machines compressor, flow of gases through openings like nozzles. The flow in which the density is constant for the fluid flow is called as incompressible flow. For example, flow of liquids, flow of gases in fans and blowers. The flow in which the fluid particle while flowing along streamlines, also rotate about their own axis is called as rotational flow. Example is motion of liquid in a rotating cylinder. The flow in which the fluid particle while flowing along streamlines, do not rotate about their own axis is called as irrotational flow. For example, Flow of liquid in an emptying wash basin. The flow in which the velocity is the function of time and one space coordinate, is called as one-dimensional flow. The flow through pipe is considered as a one-dimensional flow. The flow in which the velocity is the function of time and two space coordinates is called as two-dimensional flow. Viscous flow between parallel plates is example of 2D flow. The flow in which the velocity is the function of time and all three space coordinates, is called as three-dimensional flow. The flow in converging or diverging pipes or open channels are 3D flow.
So students, let's have a look at what are internal and external flows. So in internal flow, basically the fluid is bounded by a surface. Let's say you've got a pipe and then the fluid is flowing within the pipe. Then basically the pipe boundaries are basically enclosing the fluid inside. Whereas for external flows, basically what happens is that the flow is not bounded by any surface. It basically covers another basically surface perhaps. For instance, flow over a pipe or flow over something like the air flowing above your car and below your car is basically an external flow which is occurring. So that flow is not bounded by a surface. So the flow of an unbounded fluid over surface is called an external flow. And if the fluid is completely bounded by the surface, then it is called internal flow. So this is all about internal and external flow. If we move on to a steady and unsteady flow, a steady flow is a one in which the condition of velocity, pressure, and cross section may differ from point to point. So from one point to this point, the velocity, pressure, and cross section may differ, but they will not change. The conditions will change, but they themselves will not change. So the velocity from point 1 to point 2 remains same, but the cross-sectional area was changing. However, the velocity remained same. So in unsteady flow, what happens is that at any point the conditions change with respect to time. So even although the cross-sectional area is changing or not changing, irrespective of that, the velocity at one point is 10 meter per second, then at the other point it is 12 meter per second. So with respect to time, the conditions are changing. The pressure was 10 kilopascal at one point, at second point it becomes 20 kilopascal. So steady flow, the conditions remain unchanged with respect to time, and unsteady flow conditions change with respect to time. So this is the concept. Then we move on to uniform and non-uniform flow. So uniform flow is basically there is no change of fluid properties with location over a specified region. And a non-uniform flow, at any given instant, the fluid properties change with location over a specific region. So now steady and unsteady were time-dependent properties. Okay, time-dependent or independent. Whereas uniform and non-uniform flow are basically location-dependent or independent properties. So they change with respect to location, or they do not change with respect to location. So now to further clarify your concept, let's have a look at some video.
Steady uniform flow. An ideal fluid maintains the same velocity at all times and at each point. This is called steady uniform flow. The velocity is always 2 meters per second at all time and at all position. Just remember, at all times word makes it steady and at each point makes it uniform. Steady non-uniform flow. Notice how the velocity profile changes, but it stays the same quantitative value, that is 5 meters per second. So the velocity is constant with time, which makes it steady, but it is different from one location to the next. So it is not uniform. If you calculate the average area between these two velocity profile shapes, you will get the same result, but their shape is different in different location, so not a uniform flow. Unsteady uniform flow. Notice velocity of fluid is not constant in same tube. From 0 to 2 seconds, it is flowing in and out with 2 meters per second, and again from 2 to 4 seconds, it is flowing in and out with 4 meters per second, so velocity is changing with time. This makes it unsteady flow. Even though velocity changes, it is flowing in and out uniformly. But in this condition, The in and out position of velocity changes within the tube, which makes it non-uniform flow.
Okay, students, now that you've gone through steady, unsteady, uniform, and non-uniform, let's go and see what is viscous and what is inviscid flow. So in viscous flow, basically the frictional effects between fluid boundaries or fluid layers are significant. And basically, as you guys know already, that due to those frictional effects, viscosity is basically the property that causes those frictional effects. So viscous flow means that we are considering the fluid viscosity as a property and that is valid in that flow. However, in inviscid flow, we say that the frictional effects between the two layers are negligible or almost approaching zero. So when we say that the friction is approaching zero or it is negligible or it is not significant, then it means that we can say that the fluid is inviscid. It means that the viscosity effects are negligible. So these things are very important when we talk about turbine blades, where we need to understand that where is the viscous flow region and where is the inviscid flow region. Okay, this is also important for flow through pipes. Here you can see in a pipe that we have got a viscous flow region, and then we have got in the central line we have got inviscid flow region, where the velocity effects are, or the frictional effects basically are negligible. So when the frictional effects are negligible, but then obviously we'll have a uniform velocity profile in that region. So this is something that we will learn in chapter number 6 of your book. So this is viscous and inviscid flow. Let's take a look at a video, and you can see the effect of viscosity, that how as the viscosity increases, how the fluid behaves. So this is basically a fluid which is basically being splashed on a surface. Now the viscosity is increasing and you can see the restriction in fluid, how the fluid wants to uh, attach to itself, and then due to the viscosity it does not move as freely because of the frictional effects. Now let's move on to compressible and incompressible flow. So in compressible and incompressible flow, basically what is incompressible? The flow is said to be incompressible if the density, okay, how much is the density of the fluid, a gas or a liquid, if it remains constant, okay, if the flow is moving, if a fluid moving and the density is 1000 kilogram per meter cube, and then again later on after some point, after some time, the density is also 1000 kilogram per meter cube, then it is incompressible flow. That is why we assume in fluid mechanics problems usually that the flow is incompressible. However, there are certain cases in which the fluid can be compressed. Let's say if we take an example of a gas as a fluid, and if we are moving the gas at zero point 0.3 Mach number. Mach number is basically the speed of sound. So if the fluid is moving at gas are moving at zero point 0.3 times the Mach number, then basically the gases tends to compress. When the gases tends to compress, then it means that the flow or the fluid is incompressible. So it is important to know whether the fluid is compressible or incompressible, because then all the applications of fluid mechanics, numericals, and the theory then becomes different for both of them. And when we talk about compressible flow, then usually we are looking at the subjects like gas dynamics. So you can learn about compressible flow in another subject, which is gas dynamics. Next, we move on to natural and forced flow. So obviously, as the name suggests, in natural flow, basically the flow is because of the natural circumstances. Let's say the gravity is causing the fluid to flow, then this is natural flow. Flow. If buoyancy are the case which is causing an important role, and then basically this is natural flow. For example, a warming fluid rises in a container due to density difference. As we saw the air balloon, the hot air balloon example, the hot air how the hot air behaves in that circumstances, that is due to the buoyancy that the convection or the movement of the air take place. So this is also an example of natural flow. However, if we ourselves force a fluid, let's say I attach a pump to a pipe and then I try to move the fluid, then this is an example of forced flow. I've got a blower. The fan is an example of a forced flow. The air conditioner blow is basically an example of a forced flow. So in forced flow, the fluid is flows to flow over a surface by an external means, by an external energy such as pump or fan. So now let's take a look at fluid flow, different types of flow based on the flow patterns. So students, let's take a look and let's understand what are different flow patterns. So basically, it is important for us to know whether what is a smooth flow, what is a wavy flow, and what are irregular flow. We should know and we should understand how to characterize them. So basically, in 1880s, Osborne Reynolds he devised a system. He devised a parameter called Reynolds number, which we can basically categorize what kind of flow is laminar, transitional, or turbulent. So a Reynolds number basically help us predict flow patterns in different flow situations. So at low Reynolds number, what happens is that the flow is dominated by laminar and straight flow, sheet-like flow. So if you see in figure 1 as well, you will see that the flow is straight and it is sheet-like. It has very small amount of disturbance. However, at a very high Reynolds number, if the Reynolds number increases to greater than 4,000, then what happens is that the fluid becomes extremely wavy, internal mixing occurs, waviness occurs, and perhaps eddy currents are generated. So the fluid direction changes rapidly from here to here and then from here to here. So there is a jumbleness, there is juggling around within the fluid. So that is characterized by turbulent flow. So the turbulence results from difference in fluid speeds and direction. So one particle or one layer is moving in different speed and the other is moving fast, and then one is moving in this direction and the other is moving in that direction. So these basically create energy, perhaps significant energy loss as well. So Reynolds number basically is the ratio of inertial force to that of viscous force. Uh, and if you see at figure number 1, then laminar flow basically occurs where the viscous force are dominant, whereas turbulent flow occurs when the inertial forces are dominant. Reynolds number has a lot of applications such as that of flow within a pipe, okay, or flow over an aircraft wing or over an aircraft turbine within turbine. So these are very important applications of Reynolds number. And if you see Reynolds number formula, it is rho Vd over mu, where rho Vd is basically uh, the ratio of inertia. So the upper value is inertia and the lower value is viscous, because it is viscosity at the lower. So let's have a look at a video. So if you see in this animation, you can see that the candle is very stable and uniform. This is an example of laminar. However, if it is stable but wants to basically becomes wavy, then it becomes transitional. So it is basically transitional flow is basically an intermediate flow between laminar and turbulent. And then you can see the turbulent, how wavy it is, how irregular it is. So please go through this video, another video in which they have carried out an experiment to show you how the fluid moves. They have basically put a dye and ink within a flow of water to visualize how the flow is basically occurring in laminar, transitional, and turbulent flow. Okay, students. So now we move on to fluid description. How can we describe fluid? How can we describe the properties of fluid? So basically, there are two approaches. Number one is the Lagrangian description, and number two is the Eulerian description. So what are these types of description? Basically, we need to visualize the flow. We need to understand how the fluid moves, how the fluid behaves, and how to identify the properties of fluid. So in Lagrangian specification, basically, the flow field is basically a way of looking at a fluid motion. So I'm going to look at a fluid motion where the particle is moving and I'm also moving with the particle. So the observers moves or follows the individual separate particles through space and time. So plotting that position separately. So if I'm plotting I'm observing and I'm plotting that individual particle through time gives me the path line of that fluid or that fluid particle. So you can also visualize this based on snooker ball. So basically, how the snooker ball basically moves, okay, and you're basically following. Your eyes are following that single particle is basically an example of the Lagrangian approach. So Lagrangian approach is basically a microscopic point of view that you basically follow a single particle. And then if you got many particles, then you have to follow each particle separately. So it becomes very complex. So in real world applications, if you want to observe fluid flow for a large number of particles, then this approach becomes very difficult. So here is an example of Lagrangian description where your eyes now, if you see the screen, then your eyes are following that path. So you are basically the observer and you are basically moving with it. And then you are noting the properties of with the by following them. So this is Lagrangian description. Now what is the other one? The other is Eulerian description. It was introduced by Swiss mathematics Eulerian. So in Eulerian description, basically what happens is that you identify a flow domain which is called a control volume. Okay, so what happens is that I've got fluid. Okay, so what I'm going to do is I am going to define a control volume here. Okay, so this is basically my observation area. Now my eyes or I'm only going to focus in this control volume, neither outside nor anywhere else. Only this control volume is my focus. Now whatever is going inside that control volume is basically a function of space and time. So the fluid particles are all basically a function of space, means x, y, and z coordinates, and the time that how they move around. So control volume is a volume in space of special interest. So this control volume which I have drawn is basically a volume of a special interest for a particular observation. So I'm going to observe this volume only. And within this volume, okay, let's say I identify this is a control volume. Now I'm going to observe the average behavior of the particles separately. So in Eulerian description of fluid flow, individual particles are not identified. So I'm not going to follow each particle separately. Okay, and the control volume was defined. So control volume has been defined. Pressure, velocity, acceleration, and all other fluid properties within the control volume are basically expressed. And these properties are expressed as a function of space and time, as you can see in the figure. In Eulerian description of flow, one is not concerned about the location of each particle, okay, but rather the velocity, acceleration of fluid particles of the behavior of that whole control volume. So we are concerned with the macroscopic approach. We are basically averaging the behavior of all those particles within that control volume. So here I will give you a video as well so that you guys can go and have more understanding of what control volume is. Now that we know what is Eulerian and what is Lagrangian approach, what are those approaches? And when we are going to follow that single particle, then what happens? If we follow that particles, can we make a streamline? Okay, streamline is the curve that that particle follows. Then what are path line and what are street line? So let's have a look at that. So a streamline is basically a line. Okay, it is a line. It is a line which is drawn based on the tangent vectors. So let's say I've got these particles, and they have got their own tangent. Okay, now a line which is tangent to these vectors, okay, is called a streamline, and the tangent to the velocity vector at any given instant. So a streamline is basically an instantaneous pattern at that time. So if let's say my particle moved here, then my streamline might becomes like this. At that time, this is t is equals to 1, and here the t is equals to 0. So a streamline changes with respect to time. So if you consider this simple shear flow example, which we have already done, okay, then the fluid is moving because of the upper plate is moving, okay, and then slowly the other layers are also moving in this direction. So the streamline is following the part of the velocity vector. This is the velocity vector, and streamline is following that path. Now, what is streak line? A streak line is the locus of the particles which have either earlier passed through a prescribed point. So this my particle basically is here. Then after some time it was here. Then after some time it was here, and then after some time it was here. So it is a locus of the line where the particle had moved earlier on. So time 0 here, 1 here, time is 2 here, time is 3 here. So I'm going to basically plot with respect to where the earlier the position of the particle was, and then I'm going to draw a locus of particles or line through that points. Then what is a path line? A path line is actual path of the actual path traversed by a given fluid particle. So basically, for example, consider a simple shear flow. So this is a simple shear flow between two parallel plates. Okay, a path line is the actual path which the particle took. So these things are basically for steady flow. Okay, for steady flow, path line, streak line, and streamline are all same. Okay, they are all same because they are following the same vector or tangent, and they're following the same locus of particle based on the previous time, and then they are following. Then they are also following the actual path. So they are all same if the flow is steady. So flow visualization with respect to path line, streak line is very important for us in engineering applications. So basically, if you got a wind turbine blade pattern, so this is a pattern of a wind turbine. It can be a pattern of a airplane wing. Okay, this is called an aerofoil. Okay, so this is called an aerofoil shape. So you can see that we have got streak lines over the fluid. Okay, the streak lines are basically over this fluid, and they are colored. So in the previous video example, you have seen that we can inject dye within a fluid to observe its path. Then we have got smoke streak lines, okay, here as well. Then we have got a schlieren image, okay, refractive flow visualization. So here you can see a man who is basically doing a barbecue, and you can see how much smoke is being generated. Usually when you're doing barbecue, you don't know, you're just looking around and partying, but you can see how much amount of the smoke cloud that you guys are forming. So schlieren photography is basically used to visualize flow patterns. So they are basically different types of techniques, and they are basically, if you see while barbecue you cannot see the gas flow, right? But if you are going to use a schlieren image, basically what happens is that the gas has a different refractive index. Okay, so when the gas has a different refractive index than the air, then it can basically make a contrast. So Selenium image are basically shades of gray. So you can see this is a different gray color and this is a different gray color. So based on the reflective index difference, it can basically form images. So this was all about flow visualization and flow description. Next, we are going to look into control.
If there were a portal through which you could see all of the invisible air currents, temperature gradients, and differences in pressure and composition of air, then this is what it would look like to strike a match.
This is helium being squeezed out of a balloon.
You could see the warm air rising off your hands. The invisible vapors of isopropyl alcohol and the plume of ejected material when you sneeze.
Okay, students. So previously I mentioned about control volume. So control volume is basically a part of fluid flow system. In a basically when you want to study or when you want to make an observation, basically there are three different things. One is the system that you want to study. Then what is outside the system is called the surrounding, and then the boundary that separates the surroundings and the system is called boundary. So we have got three things: systems, surroundings, and boundary. So let's take a look at this example. You have got a bicycle pump, okay? And in this bicycle pump, if I want to visualize the fluid inside, then what I'm going to do is I'm going to basically create an diagram, and in that diagram, I'm going to identify the system. So the system is basically the part which is basically by the control volume, or the system is basically what I want to observe, the region which I've chosen for study, okay? And then the boundary is basically the boundary which is basically separating the system and the surrounding. Now the system can either have an inlet and outlet, or it does not have an inlet and outlet. So if a system does not have any inlet and outlet, then it is called a closed system, okay? And in a control system, a volume, a closed system is that system in which the mass cannot exit outside, okay? The mass cannot cross the boundary. Remember what I told you about the boundary, and the mass is fixed, okay? For example, you've got a water bottle and it is closed, so the mass cannot exit or enter, but the volume might change, okay? So let's say you've got a gas, and then the volume of the gas has changed upon heating. However, the mass remains constant. Now let's take a look at open system. So in open system, the control volume, the capacity is controlled, the mass and energy can move across, and the mass flow is available. What does it mean is that the mass can flow in and go out, okay? However, the capacity, mass is going in and out, so the boundary is basically moving as well. So the control volume boundary, as you can see, is moving. The plunger is moving up and down as the mass comes inside. So for open system, there should be at least one entry and one exit. The moving boundary can be seen for closed system as well. However, there is no entry and exit. So the selection of control volume is very, very important. You should know whether you are selecting the correct control volume or incorrect. Incorrect or wrong analysis will occur if you're going to select the wrong control volume. Let's take an example. You have got a two inlet and two containers, and in these two containers, you've got different types of inlets and outlets. Now, if I'm going to select them all together, then I'm ignoring this inlet outlet of this part and inlet of this container. However, if I separately select the control volume for each of them, then I am basically observing all the inlets and exit together. So it is important to select the control volume correctly. So this was all about fluid flow, fluid description, different types of flows, and then what is system, what is surrounding, what is control volume. Next, we are going to study the conservation of mass principle, conservation of energy principle, and conservation of momentum principle.